organizers for the invitation. In particular, I also want to thank the research station here, because, I mean, if it wasn't for my interaction with Paul Wigman at a previous meeting, I would also not have been here. So it's lots of very interesting activities going on here. So the talk is on anisotropic quantum Hall droplets, and it's based on joint work together with, well, Lagorgi is giving a talk right now, Bastien Lapierre, who is unfortunately cannot be here, Jean-Marie, and Benoit is also in the audience. And it connects closely with what Lagorgi talked about in the third part of his talk. So I will, in a sense, provide some of the details that he couldn't go into, and then extend to many-body properties. So, just to restate the setting, Moosavi, non-interacting gas of electrons in 2 dimensions. Write down the one-body Hamiltonian, so you have the Landau part in a strong magnetic field, and you have a confining potential. That's on top of this usual Landau part. And the potential will be assumed to be, in general, anisotropic. So that's the question. Starting from this kind of microscopic description, we would like to derive the many-body physics and eventually the effective edge theory on this droplet that's confined by this anisotropic potential. And since we're in a very strong magnetic field, we restrict to the lowest lambda level. So everything in this talk will be about lowest lambda physics. So, as I mentioned, the strategy is basically be to first compute one body or one particle spectrum, one particle wave functions, and from there continue with many body functions, many body observables. Okay, so the assumption, as Lagorgi also mentioned, V of x would be monotonous, meaning that it has a unique global minimum, and all the level curves are nested. So a level curve for, well, they will be containing each other as in this picture. And in that sense, or giving that, you can always find error-preserving diffeomorphisms that map these level curves to a circle, and that's kind of what we'll be using. But in a special case, as motivated by Lagorgi, we will consider so-called edge deformations. And these are conveniently written in polar coordinates, where, well, if I have polar coordinates r and phi, then an edge deformation is defined by mapping r to r over square root f prime and phi to some f of phi, where f is a circle diffeomorphism. And you can easily check that this preserves the area form. So now, so that's our edge deformations, and one way to write them is that, okay, now we write everything in polar coordinates, everything depends on r and phi, and the potentials will be of this form. There's some function v naught of the combination r squared over 2f prime, which is essentially will correspond to some action variable. So it's a convenient choice, but you could have written it in a different way. But it's conveniently written as a function of the action. Okay. Let me introduce magnetic length, because there will be an important length scale in our problem. So it's proportional to the, well, h bar, I mean the square root of h bar over qb. Q is the charge of the electrons. So this would be a small parameter, and the assumption will be that a potential V is weak relative to this magnetic field. So in a sense, the important part is that it varies slowly on this length scale. So we can treat it perturbatively. So as motivated by Lagorgi, we will project the many-body, or the one-body Hamiltonian to the LLL, and in that sense, or in the LLL, well, it's only the potential that acts as an effective Hamiltonian. Since, I mean, the kinetic part just gives a zero. I mean, it's just in the low. Otherwise, you would have some other term here. So the problem we would like to solve is exactly this eigenvalue problem. We want to find this phi m eigenfunctions, or the wave functions, and the corresponding energies em. And in general, you have to resort to some semi-classical approximation, or some way to proceed. In the isotropic case, well, you don't have to, so I will review that briefly. But in general, SMR classics or something else is needed, and that's not necessarily new in literature. It has been studied or has been used previously, but kind of what can motivate to be new in this talk will be the WKB ansatz for the wave functions that Blagoje highlighted. So the claim here is that, well, in the isotropic case, angular momentum would be a good quantum number to use. In this case, well, since you break rotational variance, angular momentum is no longer, it's not longer a good quantum number in the original sense, but there is a generalization of it that is a good quantum number. So this M can be used to label each state, and it generalizes the angular momentum, and essentially it labels the area of the level curve. It labels the level curves that enclose a certain area, and that area is exactly 2 pi L squared times M. Okay. So I will first kind of explain the many-body results using pictures, and then I will show you how you get these pictures from our results, So these are all plotted using the one-body results that I will show you. So what you will find, so for the potential I actually showed on the previous slide, or 2 previous slides, we will construct the density, and you will show that, or we will see that this constant in the bulk, and then you have like a error function decay along the edge. The current we will show by explicit results that is localized on the edge of the droplet with a Gaussian decay away from it. And correlations will also show that, well, here I'm trying to plot 2-point correlation functions. You put 1 point at this x here, and then you vary the position of the other field about x and y. And then you will see, I will show explicitly, that it decays as a Gaussian away from the edge, but along the edge you have a long-range interaction, or a long-range decay, algebraic decay. But I mean, we'll revisit this picture later. So this kind of highlights, yes?
In many body, you mean that there is interaction between electrons, or
no, not interacting. But you sum up all the contributions.
Yeah.
Yes. I mean, we would like to do interacting, but that's for the future. Okay, so to have a kind of motivating remark, one reason I got interested in this when talking with Blagoje was that, well, I've been very interested in studying conformal field theory, where you deform it in some way. You deform it by changing the propagation velocity from some constant to a function v of x. So here I write down such a theory that's chiral, so it's only right numbers, say. And you can write it in general as some Hamiltonian. The Hamiltonian is some integral over the stress energy tensor multiplied by this v of x. And this guy here is essentially the Virasoro generators, but in position space. So this is the Virasoro algebra, where you have the central charge C. And this has been studied, well, a lot in literature, including by some of my collaborators. So Jean-Marie, Jerome, in an earlier paper here, also by me together with Dubai and Pascal Carleves and others. And I also want to take the occasion to highlight the importance of, well, an early collaboration with Krzysztof Gawecki was very influential in how me and my collaborators approach the problem, which is to study diffeomorphisms, which again reconnects with what we study here for quantum Hall droplets. So in general, you can study this Hamiltonian by constructing some diffeomorphisms that, when you represent on the Hilbert space, allows you to map this deformed Hamiltonian to something that is homogeneous. So here you can find some V naught, which is a constant, that gives you a homogeneous conformal field theory. Plus constant. And using this unitary operator, you can also compute correlation functions. For instance, you can compute whatever you like. As long as you can compute it in the undeformed theory, you can compute it in the deformed theory. And this can then be used to, as I said, correlation functions, and then you will find that this deformation gives a trace, it gives rise to some prefactors in the correlation functions, which is, well, we will see later on that we were interested in computing correlation functions for the quantum Hall droplet on the edge, and one of the interest was that, well, is it possible, or is it not an inhomogeneous conformal field theory that describes that? So that was one of the motivations. We will see how that gets resolved. Okay, so that was kind of the plan of the talk, or here comes the plan of the talk. I will first begin by reviewing anisotropic potentials, and then continue with edge-deformed potentials. I will tell you about the details of the one-particle results, and then the many-body observables that you can compute from those. And in the end, if time allows, I will explain the effective edge theory and in particular how you obtain it. Okay, so for anisotropic potentials, if you have a very strong magnetic field, B, as Blagosi also mentioned, the wave functions when the potential is anisotropic is essentially given by the usual wave function for the pure Landau Hamiltonian. So it is this known shape expressed in terms of a complex coordinate that is, well, dimensionless. So in particular, this has a Gaussian, well, it decays as a Gaussian away from the maximum, which is on the equipotentials, which are now circles, gamma m. So it's, these ones are centered on a distance square root of m away from the origin. You can also use then these to construct the projection operator to the lowest Lambda level, which has a kernel, everything here. And this will be used later on also in the deformed case. So in a sense, these wave functions are a good candidate in the anisotropic case. However, the eigenvalues will be different, or I mean, you now have corrections to the eigenvalues from the pure Landau problem, and these are then the energy eigenvalues that's due to the potential contribution. And
but these are only approximate eigenstates if you have a potential.
Yeah, it's perturbative it's true in the sense that the potential should vary slowly compared to magnetic length. Yes, which we assume everywhere in this talk. So yes, it's approximate. Okay. It's, let's see, the word exact is perhaps not the optimal choice. It's more exact than in the sense that, well, in the general case, I'll have to do another expansion. And so here, this is the full sum of that expansion for the anisotropic case. However, it is not, it's still perturbative in a sense of how the potential contributes to the eigenvalue problem. Yes. Okay, so, but here, oh yes.
Can you comment on the choice of the angular momentum eigenstate to begin with compared to coherent state that look like the semi-classical particle that I would put in my potential to begin with?
Okay, I'm not sure I understand.
Is it because it eases the computation? Because in the anisotropic case,
symmetric, so
it's
to diagonalize the angular momentum.
So
here
in this case, the angular momentum is a good quantum number.
yes.
So that's kind of what we hold on to, and that's why this is a good candidate. I mean, you can verify that will be the eigen.
But in the anisotropic case?
Yeah, in anisotropic case, this comes in the next, in a future slide, and then I will tell you how you have to generalize this. And I mean, it was in a sense highlighted or mentioned by Blagosi already. Yes.
My understanding, the semi-classical approximation is not a limitation. It is automatic when you take a very large droplet. So you say, okay, I have a large droplet, so I take many electrons or a large radius. Then this comes automatically when you expand for large radius. So, and then the magnetic length is small. So, and this is important because you want to study an edge effect on a large droplet. Yes. So
yes. I mean, I will actually refer to your work in the.
So I will talk of this. In fact, there are two different regimes that I will talk, and I think it's not a limitation. The semi-classical expansion.
No, it's not a limitation. You mean the expansion in small l?
Yes.
Yes. No, not in that sense, but here I just want to say that well, you can do it you don't have to do the semi-classical expansion in order to write down these eigenvalues.
Yeah,
But in the anisotropic case, that's what we have to resort to. There is no such nice formula as here. It's another nice formula.
my statement is a positive one.
Yes.
Is not a limitation, the semi-classical approximation. Is physical expansion of a large droplet when you study a region around the edge. So you take a finite region around the edge, and then you send the size of the droplet very large, and then you get this expansion immediately.
Point of
Oh, yes. Well, okay. So in this case, we have this expression, and to anticipate what we have to do in the anisotropic case, you can already at this level kind of reproduce the semi-classical expansion by saddle point approximation. So you can rewrite this as you expand in L squared, and you find the contribution from the potential, or like the times kind of a gradient expansion. So gamma m is the first derivative of the potential, and omega m is first, and then the gamma m is the second derivative. And this is like the second order contribution in L squared. So I will show you in later slides how you generalize this to the anisotropic case. Okay. Now, one thing that will be of importance for us is to study, as I mentioned, many body physics. So you consider a droplet of many electrons, large n, and you sum up all the contributions. So you can define the one body density matrix, as usual. And since we have explicit expressions for the wave functions, you can plug those in, and you find the following expression that can conveniently be expressed in terms of an incomplete gamma function. So that's kind of the result. And now, in order to extract how this behaves close to if you put these 2 points x1 and x2 on the edge, you can use basically properties of this incomplete gamma function and a saddle point analysis to show, as is done in an appendix of this paper here by Capelli and collaborators, to show that the correlation function behave in the following way. So it behaves as 1 over sine of the difference between the two angles if you're on the edge of the droplet. I mean, it's a circle, right? And this is the same correlation function you will find from chiral conformal field theory. So that's one diagnostic tool you can use to see what is the effective edge theory. And so later on in the talk, I will show how this generalizes to the anisotropic case. Do you have a question?
Well, if there are no interactions, we know the edge theory.
Yes, so I'm just restating the known result. This is a review part. Yes. Okay.
It's just because you talked about diagnostic tools.
Ah.
I mean, we know the disease, so
Yes.
we don't need diagnostic tools.
Yes. Okay, but it's if you wouldn't know, then that's something you look at. Okay, so for deformed potentials. So recall that we consider a particular class of deformed potentials. It's a shape where, it's given by an edge deformation. And it becomes natural to work in action angle coordinates, so canonical action angle coordinates. So introduce a dimensional action coordinate, k, just kind of get rid of dimensional quantity L squared, and an angle phi. And these are defined as, these are defined with respect to the potential, and so this quantity in here is basically L squared times k, and your angle coordinate is this f of phi, where f is the diffeomorphism that used to define the potential in the first place, or rather f prime. Okay, and if you have these two coordinates, you can also go back to Cartesian coordinates. So I just write down what these things are. I mean, we don't have to go into some expression, but capital X and capital Y, these are now functions of k and phi, and it spits out the Cartesian coordinates. Okay, so I will now give you the same ansatz that Blagosia highlighted or mentioned. So we would like to construct an ansatz for the wave functions that solves our eigenvalue problem. And the way we proceed is as follows. We consider some state that's localized on the equipotential gamma n. So for a given generalized angular momentum quantum number, we construct this state. There is a phase factor, basically indicate. It describes how this the winding of the state, which is m, and then there is this part, this function n of theta, which is an unknown function, and then you have to integrate over theta, and then some dimensional thing. So the important part is that the winding around the exponential is all contained in this e to the power I m theta. So n of theta doesn't wind. And then in the end we need to project this to the lowest lambda level, which is gives us the following wave functions with the projection.
So this now the projection is a coherent state, or
it's the same projection operator as
but the result, right? You're taking some kind of delta function, right? This xy.
It becomes a delta function in the limit when L goes to.
No, but what is x? What is the cat? What is
Yes. It's a Dirac. There's a Dirac on the.
And then you project it to the lowest level, and it becomes a coherent state, or not?
Yes, you do.
You get the
becomes
knowledge.
something you can construct
You don't have to
composition
project.
of coherent states. Is that correct?
I mean, when you introduce action angle variables, you think of, that the two coordinates in the plane become non-commutative in a certain sense. And, yes. So the x and the y are what?
These? Yes. They are just. So since I describe everything in action angle coordinates, I need to have. I mean, it's just a function that allows me to get back the corresponding Cartesian coordinates, and so this is just this thing. If I were to, this state is localized and on the edge. So it's a delta function.
That state is a state in a full Hilbert space, right? Before projection.
Yes, exactly. Yes, yes. And then you need to project it to go to the lowest lambda level, and that's when we have the candidate wave function. So the important part here is that it also decays as a Gaussian away from this level, but with some other ingredients in here. And you can verify that this will give you the usual lambda wave functions in the special case of an isotropic trap. In that case, this...
On the right-hand side, e to the power minus z2 over 2
Yes.
is the only z dependence?
No, there's also Z dependence here.
Oh, okay.
So that's important. So you can verify for yourself that, okay, in the isotropic case, n should be constant, so this is just some proportionality thing. Then expand this, or an f prime is just 1. Now you can expand this, and then you can find that it becomes exactly after carrying out the integral, it becomes exactly the lambda wave functions. So that's the generalization, and it maybe answers your question also. So that's our candidates. The important part is that you need to introduce this n of theta. Okay, so why this wave function? So in analogy with WKB, so in the usual WKB ansatz, you have this exponential ansatz with the classical part, the first quantum correction, and so on. So essentially, what we need to introduce, or I mean, I will try to highlight that our contributions, this e to the power I m theta, it corresponds to the classical part, and this function n is the first order quantum correction.
You can refuse to answer, but we have, for a particle in a magnetic field, we have two sets of canonical variables, the pi1 and the pi2. These are the covariant, the velocity operators. Okay. They don't commute. And then we have the guiding center coordinates, which also don't commute. If you now talk about angle action variables, which variables are you referring to?
I am referring to variables that is canonical in the sense of the trapping potential. So in a sense, they'd be natural to pick in order I mean, with respect to that to the overall confining potential. Perhaps.
As I said, you can refuse to answer. And
It's
you,
projected to the LML, so the kinetic part is dead. So you're only left with actual physical.
guiding center
Guiding
coordinates.
center, yes.
Okay. I mean, I'm not familiar with the terminology, so.
Oh, I mean, of course you're familiar.
Guiding center. No.
Well, if you have a classical particle, a constant magnetic field, it moves along a circle, and the center of this
Yes.
circle is the guiding center.
So, as also known from the usual WQB answers, is that this first order correction, S1, should satisfy a transport equation. And so our aim here, or one step, is to construct the corresponding transport equation for this function n of theta. So that's kind of the motivation for why we made the ansatz as we did. And it also highlights why it's important to introduce this function. Without it, you'll be missing the first order quantum correction, and then you're missing you will not be expanding things properly if you're not including it. Okay, so recall what the eigenvalue equation is. It's this PVP, and you have the wave function. So this we know, we have an answers for. We have the energy, which is also known in the sense that, well, it should have this following expansion where there's an unknown constant, or there's an unknown object, this first order correction. So we have two unknowns. We have this EM, first order, and then we have the function n of theta. The only thing you have not spelled out is this PVP operator. So what is it? So, well, I've just stated as a result. So it's, we need to expand it also now in L squared, and it's known result how this expands. So it's basically a gradient expansion of the potential with a contribution that comes from the projection to the lowest lambda level. So this is kind of based on results that we learned from papers by Long and Shah. I mean, it's one of the who has been working a lot on this. So we derive it, but I will not go into the details of how we obtain this expansion. So now we have basically everything, and you essentially plug everything into this eigenvalue equation and restate it as a problem. So the problem is now find is n and this first order correction to the energy such that this eigenvalue problem is fulfilled for all z in the complex plane. So that is the basic problem. And solving that gives us the eigenvalue, the one particle spectrum and the wave functions in a semi-classical approximation. So that carries over to the next part when we try to solve this. So just recall that that's not going into the details, but that's the equation we need to solve. So the strategy is that, well, in general it's really complicated to solve this, but you can do something that simplifies it, and that is to consider z that lies on level curves. So the level curves some large number m, and then you can basically in the complex plane you can write down how this z traces out the level curve with some angle alpha, and if you then evaluate this equation on that z, then you know that it will be valid for all z by basically holomorphicity. So then you can infer that it will be true in the whole complex plane. But it allows you to kind of simplify your computations. And if you do that, and that's a lot of work, you find eventually a transport equation for this function n.
So
Yes.
it's a very stupid question. So you have n of f of phi, and you want your functions to be functions of phi and not of f of phi. Is it a better strategy just to know? I mean, it's not like if I change the argument to f of phi, that wouldn't give nicer formulas.
It's just that the formulas were nicely written in this, but the function we wanted is n of theta, but theta is f of phi, and f is given by the potential, so you can go back and forth.
Okay.
So f is given, and whatever is more convenient, we use.
And you're saying this is more convenient.
This turned out to be more convenient. So what we find is so now the results will be somewhat lengthy, but you can conveniently split it into two parts. So you can consider, well, the norm of this function and the phase, and you just state them separately for these two. So we start with the phase. So the transport equation becomes an ODE for the phase that has the following expression. So again, this is a lengthy formula, but important part to note is that, well, most of these terms are just derivatives of some function, so you can easily integrate it. The only exception is this part. So you can quickly integrate this equation, and you find what theta of phi is. And we know that this n should not wind when you go around the potential, so the boundary condition should be that, well, that's also not true for phi. So integrating this and using this condition will give us a condition on the energies that appear explicitly here. So then just integrating and reordering gives us an explicit expression for the first order correction to the energies.
So
Yes.
the things that easily integrate don't involve the potential, right? You said there are some terms. Which
Yes,
easily
I mean
integrate.
all these terms. I mean they don't involve they involve the function f that is used to define the potential, but
But they don't involve the function v at all.
no.
Right? Okay.
V is in this gamma of m, or gamma m, omega m, and, well, I mean, by consequence, also in the energy. So, yes. And so that's the first order quantum correction to the energies. And it's a simple check. I mean, if you were in a homogeneous, in an isotropic case, this f double prime is 0, and so you recover the formula I showed on a previous slide for isotropic result. So that's the energy. So that's one of the two things we need. The second thing is the norm, and this one, well, you have to work, and then you find the following differential equation for the norm, which you quickly integrate to find that it has this following shape. It's some normalization times this combination of f prime and f double prime. And to anticipate results later, you can just introduce this function sigma of phi, as it will appear as a width, and so this is basically the expression inside the square root.
And the norm does not depend at all on the potential. Any comment on that? Oh, okay.
So, not
forget it.
not
I mean,
necessarily.
at some point, right? Like there are two parts. One part is universal and is independent of the potential, and there are some things, I don't know, are they corrections or not corrections? But in the phase there is some influence of the shape.
Yes. And yeah.
And it's again that the potential is varying very slowly in value, and the eigenfunctions are more or less concentrated along equipotential curves. That's why the potential doesn't appear explicitly.
Highlights how you will on which length scale or how it decays away from the shape of the equipotential. Okay, so with that in mind, now we have all ingredients.
May I say something? Why don't we let the speaker make his point till the end of the seminar and ask afterwards? Because this maybe not very convenient for a seminar, all these interruptions.
It's up to the speaker to accept or not to accept.
It's okay. So, now returning to the expression for the wave functions. So we had the following ansatz. I'm just restating it, and again, just highlight that is something that you expect to be true for large quantum numbers then. So now we know what this n of f of phi is. So you can plug that in, and you can do a saddle point approximation. So this will have a unique saddle point, and starting. So let this Z be centered on or localized on an equipotential corresponding to M, and do a saddle point approximation. Then you find the following expressive expression. So this is also shown by Blagoje. So you will have explicitly now the Gaussian decay. A is kind of the deviation from the equipotential, and then you have some phase factor that involves, well, the winding, and also this WQB phase, which implicitly, but you can see it explicitly from, well, the differential equation is integrating it once. And then there's another phase that just kind of comes from that. Well, there was some, actually, you can have some imaginary part here. I just moved it into the phase. And you also normalized it such that, well, in an obvious way. So that is now our wave functions. So this is true up to higher order corrections in M. So yeah, that's one of the main results. And yeah, now you can use it to plot what the density is, I mean the corresponding density to one particle state is. So in terms, if you have elliptic shape of the trap potential, you will find that, well, the density is peaked at the points where you kind of pinch the shape of the potential, and if you have some arbitrary shape that actually corresponds to the one I had in a previous slide, then you get this kind of mountain range shape. So now from our explicit expression, you can compute all this, plot all these expressions, or plot all these contributions. So that also then carries over to many-bar results when you sum over all these contributions. So again, consider a quantum Hall droplet that's in this confining potential that gives us this anisotropic droplet. Assume now there's n particles in there. What we want to compute is well, first of all, the density. So just summing up all the contributions from the one particle contributions. Well, this is exactly this expression we want to compute, and plugging in our approximate or approximate wave functions, I mean, it's given by the semi-classical expansion, you find the following expression, which we now would like to carry out the sum. And each of these contributions are centered along their own equipotential. So to do that, we try to do it both for the regime where you're in the bulk and at the edge at the same time, just by changing where your overall coordinate x is located. So you can parameterize it as follows. So write it, let the set coordinate, the compass coordinate corresponding to your point x be given as follows, where you let it be at some equipotential I call mz, and if mz is equal to n, you're at the edge, and if it's much smaller than that, you're in the bulk. And so you do that, and then you change the summation variable from m to this small k, so you're kind of considering deviations away from this point mz. And then if you use the Euler-Maclaurin formula for this expression, you find the following results. So plug that in to the change of coordinates, and the Euler-Maclaurin then gives you that the overall expression is given by a complementary error function. that depends on the deviation away from where you are in the bulk or along the edge. And so, as two special cases, if you're in the bulk, then your momentum label is your quantum number label here is much smaller than n. And in that case, that is basically dominated by this minus capital N. And so this is, well, everything in here is minus infinity, so you get a factor 2. The value error function, the component error function at minus infinity. So this is 1 over 2 pi L squared. However, if you're on the edge, so m is when the same as n, or capital N, and this thing is gone, and you have the decay that I mentioned before. So close to the edge, you will actually I have plotted here. So I mentioned the bulk value, and then if you go close to the edge, you get the complementary error function that decays towards 0 when you leave the droplet. So that's basically just plotting the result. You can do the same thing for the current. I mean, I don't have much time, so you can repeat the same step, and you compute the current near the edge, and you will find that, when not going into the details, you see that it's tangent to the droplet's edge, and well, it's as expected. It also satisfies it's divergence free, which is also then corresponds to that. Well, as I mentioned, we had a transport equation. That transport equation is, in a sense, corresponds to this divergence freeness of the current.
I mean, why shouldn't that be exact? That should be exactly divergence free. It's the approximation which does not reproduce that exactly.
So you only compute things to a certain order in square root of capital N. So I mean, the only statement we can say that it's exact up to corrections, but if you want to push it further, you can try to verify more and more subleading terms. So it's expected to be exact, but then you need to verify that by pushing the computations to higher orders in L squared, or corresponding 1 over square root of that. So I mean, yeah, to the order stated here, it's exact.
I would have said it's exact by the definition of J, not by the computation of J.
This is a verification that it's actually divergence free. So you can show explicitly that it is. Okay, and the same thing then for correlation functions. So I should spend some time on this. So defining the one-bounded density matrix as before, but now we have two different points, x1 and x2. If you zoom in near the droplet's edge, just similar computation to what I did for density. Let now this Z1 and Z2 be the complex coordinates corresponding to x1 and x2, and I'm at the edge of the droplet because they're centered, or they're located at, well, square root of n away from the center of the drop, or the global minimum of the potential. So if you do the same computation, you find the following expression for the correlation function. So, well, it's a bit unwieldy, but you have some important components. So you have essentially the expression that you expect from a conformal field theory is 1 over sine of the difference between the points. So so now, I mean, these 2 points are located on the edge, and so it only depends on the difference between the angles on the edge if you express it in terms of the canonical angle coordinates. Then you have this kind of Gaussian decay away from the edge, and these prefactors. And these prefactors is somewhat reminding of the prefactors you obtain by if you perform a conformal transformation of your theory. And so that's kind of one thing we thought would imply that maybe there is an inhomogeneous conformal field theory describing the edge. However, so I will not have time to go into details, but in order to find true edge theory, you need to sum up the radial contributions, and that exactly cancels these factors. It corresponds to those. So it looks inhomogeneous in the sense that, well, it depends, has all these prefactors, it depends on the angle where you are on the edge, but after the radial integration, all this will wash away. So that's just mention again that this is what you use to plot the result. You find the algebraic decay and the Gaussian decay away from the edge. So we only have time for one of these slides. So just to kind of explain what the edge theory is. So as I mentioned, in order to extract the edge theory or see what is the true correlation functions that corresponds to the edge theory, you need to perform this radial integral. And when you do that, you from the exact result that or from the explicit result that we derive from one-body properties, you find that everything becomes it becomes this. So it now only depends on the 1 over sine of the difference between where you are located on the droplet edge. And this agrees exactly with what one would expect, meaning a free fermion CFT, that's chiral. So, and that is the corresponding Hamiltonian. So you find that the theory is described by, well, a CFT with the propagation velocity defined by the slope of the potential at the edge. Good. Maybe nothing unexpected, but the way that these things cancelled in order to obtain this result was at least on the detail level, non-trivial. So I can not have time, but basically you can also obtain this result by essentially studying linearizing dispersion relations near the edge, and then proceeding as well in a standard way, you find exactly known effective Hamiltonian that I wrote down on the previous slide. So I don't have time to go through it, so I will just stop there and summarize what we've done. So what we did is we obtained, it's a very brief summary, we obtained the one particle spectrum, just a kind of the outset. So the idea was to, starting only from microscopic descriptions of the theory, obtain, find the one particle spectrum and the wave functions, and from there construct or compute the many-body observables and the effective edge theory. So kind of a hands-on, honest computation of the results. And so with that, I would like to thank you for your attention.
Questions?
You probably did it, but one of the ways to organize your results would be the following. Let's write effective field theory of one-dimensional chiral fermion and couple it to all possible types of perturbations like metric or field line in that case, and then external electromagnetic field in one-dimensional theory. And then basically using that you can compute. Then what I'm saying is that what you computed are the non-universal parts of that theory, which are not dictated by anomaly, but dictated by boundary potential and stuff like that. Is it possible to make one-to-one correspondence of saying that you did not just find chiral fermion at the edge, but you also found how does it couple with deviation of that boundary potential from linear and stuff like that?
So, we do find the universal result on the edge, but we then find the kind of, non-universal, but the corrections to that if you include how it depends when you have the radial degrees of freedom in there. And there you see like this
yeah, but like you have V double prime which actually renormalization of the magnetic field, right? So in this chiral fermion, it should be particular non-minimal coupling of this chiral fermion or maybe I'm missing something.
So I'm not sure I understand.
I think you'd find this in. Sorry, if I may, but I think this would affect the subleading corrections.
Yeah. Okay.
The first subleading corrections to the leading, it would be an irrelevant correction to the CFT, and that one would be sensitive to the V double prime, as you said.
You had V double prime in your wave function.
Yeah, but it's
real prime or F prime prime? You mean the shape of the trap affected, but the V as Anton pointed out, the norm of this function n was not affected by v prime at all.
Oh, okay. Yeah. But I mean, I remember that in your formulas you had v double prime in the one of the wave functions.
Yes. In the one-body energies.
Which you should, because it changes. Okay, but your boundary theory is not yet with that accuracy.
At leading order.
You had a question.
I didn't understand how the electron density looks like near the edge.
Okay.
Can you make maybe you can make a drawing on the blackboard?
Yes. Well, we have our droplet.
Let's just take a disk.
Yes. Okay. Disk, or now approximate disk. The decay is, so it's basically constant in the bulk. I'm trying to plot it. So that's radius. So it's constant in the bulk, and then it decays quickly.
You see, this is bothers me. There were calculations by Nilanjanadatta and Ferrari many years ago. They looked at just a spherically symmetric Hall droplet, and they found a little bump at the edge.
This is integer one.
Lowest number
This
is
is nu equals 1. This is nu equals 1. So that bump is for reference to 1 over 3. So bump appears only for 1 over 3 and so
Actually,
even in the Hall effect, this is precisely what we get.
They only looked at the integer Hall effect.
Even in the Hall effect,
The lowest, they see at the lowest or at the highest?
exactly what he's right, there is a number.
With confining potential, right? Oh,
Well, the
with
potential
confining
didn't
potential, it's not
enter
less.
because they didn't, I mean, just like here, it doesn't enter.
If I may, the bump does exist even in if in the integer quantum Hall effect in the you just feel one level, but it's an effect that is due to higher levels actually. There is
Okay,
a bump
but
that is due to higher levels. So when you project everything to the other level, there is no bump.
so, but what's the physical density now? Not,
Well, the first approximation.
if I could measure it, what would I see in a measurement? Would I see a little?
Depends how strong.
This I can't answer, but maybe a collaborator.
The bump is due to the v prime prime that Sasha was mentioning. When there's a v prime prime, there is a bump. So if your v prime prime is very weak, you will not see it. If it's stronger, if for some reason you make sure that it's very unharmonic close to the edge, you will see a bump. And presumably experimentally, you would see it, at least as a Gedanken.
And the other question was, so have you now been able to calculate the deviation of the edge energies from a linear behavior?
So
I mean, there were so many formulae, I could not keep track of what.
So the energies.
You showed a nice spectrum on one of the slides, but I wasn't sure what.
Yes. From here, so it's well, if you're near the edge, I mean these
That's
are
what I'm interested in, yes,
Yes.
near the edge.
near the edge. So these are the it doesn't work. I mean that is the lowest. I mean, like it's so this is the correction onto the first quantum correction to the lowest order results. So the question is.
Well, I mean, this, if you do so many calculations, you want to compute something that is useful.
So
and one useful thing would be to understand the deviation.
This function is not necessarily linear in M. Right?
Yeah. But of course, there are further terms and so on.
Yes, I mean from here you can in principle obtain higher corrections to the shape of the dispersion relations near the edge.
Mm-hmm.
But I mean everything we've done here was just basically to leading order.
So there are still various questions in the room, so let's try to keep questions and answer a little bit short.
Yes, I have a question. Also applies to the previous talk. So, what is the point of this program? I mean, the effective action, including also geometrical effects, the universal part, is known. So, you do this computation from scratch, and then you can, for example, determine the coefficients that go in the different terms, like the all current, the all viscosity, and so on, and you compute them, okay? But these have been computed by other means. So what is the plan? The plan is to find the subleading correction, non-universal correction, but they are non-universal. So for example, the explicit calculation in the integral effect may not be relevant for Laplace state or the through state of a many-body system. So because they are non-universal. So what is the plan? What is the idea behind?
One thing.
Maybe.
So one thing you can try to use it for is in an experimental setup. There are ideas or kind of realistic to assume that you can create in general an anisotropic environment. And so this, if you want to study that kind of quantum Hall droplet, then these are the corrections you would see. Another one you can kind of interesting is that in general there will be some randomness in that shape of the potential, and so here is also a way perhaps to study the effect of a kind of disorder in the shape of the potential. So that's one way by which you can try to address such questions. But in a sense, the idea is to be able to connect with, well, what would be a realistic experiment where you don't have a perfect shaped trapping potential.
More broadly, I would say that as soon as you move to the anisotropic realm, what is typically used, for example, even in the fractional quantum Hall case, is the plasma analogy. But you can actually prove in this case that the correlation function that you find is not the one predicted by the plasma analogy. It disagrees with it. Which means that if you, for example, apply the plasma analogy to discuss Laplace states, typically close to the edge, you should not believe those predictions. Because you can actually do the microscopic calculation, at least in the integer case, and you see that it disagrees. So that's a sort of literature-motivated answer. Another one that I mentioned is the hope to see actually the emergence of diffeomorphism gauge invariance, which, as far as I know, is a question. You can, of course, postulate a gauge theory, but that's a postulate. It's a dogma. It's not something you've proven. And then finally, there's actually the motivation, which is that nowadays you can actually locally image things at a scale lower than the magnetic length. And these, the density effects that Per showed are universal effects of the geometry of the equipotential on the width of the droplet.
So you do believe that the effective action that is been written with Fröhlich, Venn, Z terms, you believe in this?
Sure.
Okay, but you want to get the terms?
For example, well, that's related to the question I had for you. If you try to use the Chern-Simons action to deduce the first corrections, irrelevant corrections, the edge theory, typically the prediction you get are unreliable. And in fact, those corrections you see in numerics, because when you do numerics with the Laplace state, you have what, 30 particles, 40 particles? You're very far from the thermodynamic limit. So all the 1/n corrections which are irrelevant, you actually see them. And there are papers that actually show them and compute them. Well, no, they don't compute them. They find them.
So your plan is that although they are irrelevant, so in some sense not universal, there is some symmetry principle that can fix them or can promote them to something more physical. That's your
universal to some extent. It depends what you mean by universality. Sorry?
Is this your hope or not?
Yeah, the hope in particular is to find some degree of universality, obviously less strong than the leading terms, but there is some degree of universality even in these results. You see here, for example, everything only depends on the first and second derivatives of the potential, nothing else. So in that respect, at leading order in h bar or at leading order in magnetic length, all you need to know is first and second derivatives of potential.
Okay.
And actually, as Anton pointed out, you don't, for the normative wave function for the density, you don't even need to know that. All you need to know is the shape of the equipotential, and that determines everything at this order, at one loop order, if you will. So in that sense, it's a universal observable associated with actually your deformations. We used your papers to introduce those edge deformations. They come from your work from the 90s. They are the exponentiated version of your
We can continue the discussion.
I think we should conclude. Let's thank you.